Let's do one more here. So again, let's find the relative extrema and concavity of f of x. We done polynomials. Let's do a rational, where f of x is equal to x divided by x squared minus 1. All right. So let's start with part A here. Let's do the relative extrema. Let's not do the asymptotes for this one. Let's just go directly to the relative extrema. Okay. So again, to find the relative extrema, we have to find our first derivative f prime. But how do we find the first derivative of a function where we have an equation of x being divided by another equation of x? Let me write this. You got to use that quotient rule. All right, so let me call h the top function and g the bottom function. So h will be x, and then g will be x squared minus 1. All right, so now we got to find h prime, which is just going to be 1, and then g prime, which would be 2x. So now applying the quotient rule, we're going to take h prime times g. So 1 times x squared minus 1, subtracted by h times g prime. So minus x times 2x. All right, all over g squared. That's divided by, let's see, why is that working? Divided by x squared minus 1 squared. So x squared minus 1 squared. Okay. All right. So now let's simplify the top here. Let's distribute and combine like terms. So let's see, we're going to get x squared minus 1 minus 2x squared all over x squared minus 1 squared. Combine the like terms. Gives us our first derivative here to be negative x squared minus 1 over that denominator here. Okay. Now recall what we have to do here. To solve for the critical numbers of the rational expression, we had to set two equations equal to 0. We have to set the numerator equal to 0 and the denominator also to 0, because we got to figure out where this function will be 0 and where this function will be undefined. And whatever makes the denominator 0 makes the function undefined. Okay. Let me actually rewrite this a different way. All right, so we got to set two equations here. One is the negative x squared minus 1, so negative x squared minus 1 equal to 0. And then for the second one, we don't really have to worry about the power on the outside here, because whatever is, if the 0 is inside, everything will become 0 as well. Okay, so this would be, so for this denominator, all we have to worry about is what makes the inside 0. So x squared minus 1 equal to 0. Okay, let's solve for this first equation. So you're gonna have negative x squared, add 1 to both sides equals 1. Divide by negative 1, so it gives x squared equals negative 1. But what happens here when we try to square root this negative 1? Can we square root a negative value? No. What is the square root of negative 1? The square root of negative 1 is going to be plus or minus I, an imaginary number. Meaning, there is no values for x, there is no solution for x that will make the numerator 0. All right, so nothing will make the numerator 0 here. So let's go to the denominator now. So again, sum for x, we're going to have x squared equals 1, positive 1. The square root of positive 1 is plus or minus 1. You got to take both the positive and the negative root into account. All right, so here we have two critical numbers at plus or minus 1. Okay, so now we got to set up that first derivative test. So let's draw a number line. Draw our two critical values, which we found to be -1 and 1. So -1 and 1. And in this case, if we plug in these two critical values here into the first derivative, since these two solutions came from the denominator of this rational, then that means if we plug in -1 or 1 back into the first derivative, it's going to give us an undefined solution. It will make the function undefined. Okay, so now let's pick some test points here. Let's do, say, -2, 0, and 2. And again, we're plugging these into the first derivative. Okay, so we plug in -2 into the first derivative that we found above here. -2 plugged into the first derivative will give us -0.5 repeating. So -0.5 repeating. And if we plug in 0 into this equation, it should give us -1 over 1, leaving us with just -1. And then if we plug in 2 into the first derivative, we get -0.5 repeating as well. So look at what we have here. Before this first critical point at -1, and notice since these two solutions came from the denominator, then that means -1 and 1 are also serving as vertical asymptotes. Okay, and the solutions from the denominator, vertical asymptotes. And vertical asymptotes will always tend to be critical numbers as well. So before this vertical asymptote, before this first critical point or number at -1, our function is decreasing since the slope is negative. So our function is decreasing, hits that vertical asymptote, makes a jump, and then after that jump, after that jump at -1, since the slope is still negative based on this test point, that means our function is still decreasing, so still coming down. But then hits another jump at x equals 1, but even after that second jump, since the slope is negative, that means our function is still decreasing. So our function is decreasing before -1, after -1, but before +1, but also still decreasing after the second critical number. Meaning, do we have any change in the sign of the slope of this function? No, which means then that we have no relative extrema. Since there's no sign and since there's no change in the sign of the slope of our function, then we have no relative extrema for this function of x. There is no relative max, nor relative min. And it's not a saddle point here. Since -1 and 1 are vertical asymptotes, those are not saddle points. Okay, a saddle point has to exist as a point on our function, cannot be an asymptote. All right, but now the concavity. Ooh, the concavity is going to be the second derivative, which won't be too much fun here for this problem, or maybe a lot of fun. Because to find the second derivative, you got to take the derivative of this rational function that we found. Okay, so let me go to part B now. All right, so now concavity time. And let's write down what we have found so far regarding our function. So again, our original function of x was x squared. Wait, was it x squared or x? Let me double check. X over x squared minus 1. X over x squared minus 1. And then we found the first derivative, f prime, to be -x squared minus 1 over parentheses x squared minus 1 squared. All right. So if we want to find the second derivative, we're going to have to use the quotient rule again. Okay. So if we want to find the second derivative, f double prime of x, we're going to use the quotient rule again. All right, so let's define h and g. So h will be the top function, g the bottom function. So h, in this case, will be x squared or negative x squared minus 1. And then g will be, and it's the whole denominator. So g will be parentheses x squared minus 1 squared. All right. So now time to find the derivative of each one here. Well, h prime, all we have to do here is just take the derivative of each individual term. So the derivative of negative x squared will be negative 2x minus the derivative of 1, which is just 0, so just negative 2x for h prime. But now g prime here. How do we find the derivative of x squared minus 1 squared? Well, look at what we have. We have an expression, we have a function of x being raised to a power. How do we find the derivative of a function of x raised to a power? We have to use the chain rule, also referred to as the generalized power rule. So we got to bring the power down, multiply by the inside, decrease the power by 1 of the inside, so it'd be x squared minus 1 to the first power, then multiply by the derivative of the inside. And what's the derivative of x squared minus 1? The derivative of x squared minus 1 is just going to be 2x. So g prime is going to be 4x times parentheses x squared minus 1. All right, let's see. Do you want to distribute this? We'll leave it as it is. Let's leave it as it is for now. That should be fine. Yeah, let's leave it as it is. All right. So now, set up the quotient rule. So h prime, so negative 2x times g, which was x squared minus 1 squared, minus h, which was negative x squared minus 1 times g prime, which was 4x times x squared minus 1, all over g squared. And we've got to be careful as well. G is x squared minus 1 squared, which means on the bottom, we're going to have in brackets here, x squared minus 1 squared, squared, or double squared here. Okay. Now, for the top, we can distribute this whole thing, combine like terms, or let's try to find shortcuts here. Let's try to find some shortcuts. Look at what we have between these two set of terms. We have negative 2x times x squared minus 1 squared. And for the second term, we have negative x squared minus 1 plus 4x times x squared minus 1. Look at the binomial these two have in common. These two set of terms have an x squared minus 1 in common. So let's not distribute here. Instead, what we should do here is, let's factor out an x squared minus 1 from both of these two sets. All right, so we're going to have x squared minus 1 on the outside. And if we factor out x squared minus 1 here, I'm going to use brackets to group these, the remaining what we have left over. If we take out x squared minus 1 from this first set of terms, then we're going to be left with negative 2x times 1 factor of x squared minus 1. Okay, minus here. If we take out x squared minus 1 from the second term here, then we're going to be left with 4x times negative x squared minus 1. I've just moved 4x to the front and this binomial to the back. Okay, all over here, x squared minus 1 to the 4th power, right? Square squared gives us a 4th power. Okay, so now what we do is what we have here in the bracket. Now we can distribute this All right, so now we have a much more simpler distribution on the inside here to combine like terms of. Also notice on the outside, we have an x squared minus 1. And then what do we have in the bottom? An x squared minus 1 to the 4th power. Notice that we have a common factor numerator here of x squared minus 1. So what can we do? Well, what we can do here is cancel this x squared minus 1 with one factor from the denominator, making the denominator now x squared minus 1 to the 3rd power. All right. So now distributing the top, we're left with negative 2x cubed plus 2x, right? Negative 2x times x squared gives negative 2x cubed. Negative 2x times negative 1 gives us positive 2x. Negative 4x times negative x squared is going to give us positive 4x squared. I mean, positive 4x cubed, I mean. And then negative 4x times negative 1, positive 4x. All over x squared minus 1 to the 3rd power now. All right, so now what can we combine here? Let's see, negative 2x cubed plus 4x cubed. These two are like terms to give us, and combine them to give us 2x cubed. 2 plus 2x plus 4x will give us positive 6x over our denominator here of x squared minus 1 to the 3rd. Okay, and while we're at it, let's factor the numerator out. All right, so what do these two terms on top have in common? They have a common factor of 2 and also a common factor of x. So let's take out a 2x from the top. So 2x times x squared plus 6, or actually plus 3, I mean, x squared plus 3, all over x squared minus 1 cubed. Okay. Whew. So now inflection point times. Okay, so again, to find the inflection points of a rational expression, we have to set the numerator equal to 0 and the denominator also to equal to 0. So I'm going to set here, I'm going to put it inside here. So I'm going to set 2x times x squared plus 3, set that equal to 0. And also here, just x squared minus 1 equal to 0. Again, just worry about the inside because if the inside is 0, 0 cubed, it's still 0. All right, so solving for the second equation, let's do the second one first. So solving for the second equation, it's going to give us once again plus or minus 1. Again, our vertical asymptotes that we found from the previous part. Okay. Now, to solve for the second one, we have two factors of x here. So we got to set each one of those two equal to 0. So 2x equal to 0 and x squared plus 3 equal to 0. Solving for the first equation, it's going to give us equal to 0. But if we solve for the second equation, we're going to get the square root of negative 3. Can we find a real solution with the square root of negative 3? No, because that's going to give us plus or minus I square root of 3. So the second equation does not have a real answer, but the first equation does. So in this case, we're going to have 3 real solutions to the second derivative. Our 3 inflection points are going to be at 0 and plus or minus 1. All right, so our inflection points here are going to be at x equals negative 1, 0, positive 1. All right, so now time for the number line test to determine our concavity here. So again, we draw a number line, draw our inflection points, which we found to be negative 1, 0, and 1. And again, we're going to be testing the second derivative now. Now, you got to be careful with this part. 0 was a solution from the numerator. Meaning if we plug in 0 back into the second derivative, it's going to give us 0. But -1 and +1 came from the denominator, meaning we plug in these two values back into the second derivative, it will make that function undefined. DNE does not exist. All right, so now let's pick some test points here. Let's do -2. Oh, let's do -0.5 here, +0.5, and then +2. And again, we're plugging these in into the second derivative. And don't have too much rest. It's going to say f double, or right, f double prime -2, f double prime -0.5, f double prime at +0.5, and then f double prime at +2. Again, into the second derivative, which we found to be this above here. So plugging in -2 into second derivative, it's going to give us roughly around -1.04. -0.5 in the second derivative gives us about 7.7. +0.5, we plug that into the second derivative, it's going to give us -7.7. And then lastly, for +2, we get +1.04. Okay, so what do we see here? Well, before this first inflection point at -1, our function is concave down because the second derivative is negative. So it is concave down. All right. But then afterwards, based on the second derivative here, it becomes positive. The second derivative becomes positive after -1, which means our function starts to concave upwards. Okay. But then it hits that second inflection point at 0. And after that second inflection point, it concaves down. So it comes back down here. And then it hits another inflection point at 1. And after 1, it concaves back up since the second derivative came back positive. So it came back up. Now this is where we got to be careful, however. Again, -1 and 1, these two values that we found from the second derivative came from the denominator, meaning that -1 and 1 are our vertical asymptotes, meaning that in this case, we only have really one true inflection point, which is at x = 0. Your vertical asymptotes cannot be inflection points. Okay, so let's finalize the solution by determining the interval in which our function is concave down and up, and also the inflection points that we have. All right, so let's do concave down first. So again, our function was concave down. It was opening downwards before -1. So from -infinity until it's -1, it is opening downwards. So it's concave down from -infinity up to -1. And then it's concave down here between 0 to 1. It's opening downwards once again from 0 to 1. So our function is opening downwards, concave down from -infinity to -1, and also when it's from 0 to 1. Okay, and then it's going to be concave up here. It's going to be concave up between -1 and 0 on the x-axis. It is concaving upwards. So between -1 and 0, but also open upwards after +1. It's concave up from -1 to 0, or when x is greater than 1, from 1 to infinity. Okay. Now the inflection points. Again, here we found 3 zeros, 3 solutions from the second derivative. Our 3 inflection points are -1, 0, and 1. But again, if we try to plug in -1, so we had a x = -1, but if we try to plug in -1 to the original function, if we try to plug in -1 into our original equation here of x over x squared minus 1, it will be undefined. This does not exist. Okay. Similar case if we try to plug in +1. If we try to plug in +1 into the original function, it will also not exist. But if we plug in 0, which was our third inflection point, if we plug in 0 into the original function, which again, our original function was x divided by x squared minus 1. If we plug in 0 into this equation, it's going to give us 0. So we have only one inflection point here. Even though we found 3 solutions here from the second derivative, 2 of those were asymptotes. The only real solution that gives a real point was that x equals 0. And if we plug in 0 to the original function, it gives us 0. So our inflection point is at 0, 0. Because again, based on these 2 that we found from -1 and 1, these are vertical asymptotes. So we have vertical asymptotes at x equals -1 and +1. Okay, let's visualize this. All right, so let's visualize this equation here. So we have x divided by x squared minus 1. Okay, let's see, we find the relative minimums, we find the relative extrema, we find a inflection point at 0, 0. Let's see if this is good enough. Let's just do 10 tens for all of these and just see how it looks like. So there we have our functions. Look, notice, at -1, +1, there we see our 2 vertical asymptotes. Okay. All right, and here we have a function that's opening downwards, so it's concave down for -infinity until it hits that first vertical asymptote. And then after it hits that first vertical asymptote, it is opening upwards slightly until at some point at 0, it changes direction and comes back down, opens downwards. But then it hits that second inflection point, and after it hits that second inflection point, it has an upwards type of curve. It's concaving up. Okay, so it's concave down before the first vertical asymptote, and after that inflection point at 0, and it's concave up before the inflection point at 0, and after the second vertical asymptote. All right. So here we have looked at the concavity, the curvature of a function using the second derivative. Now, just a last set of notes here regarding the concavity of functions, specifically how it pertains to business applications. Okay. The inflection points where we have a change in concavity when it comes to business application, the inflection point from negative to say positive, when it goes from concave down to concave up. In business, that is known as the first sign of recovery. All right, so for business indicates a first sign of recovery, where the function will start to make profits or recover from losses. Okay, so like suppose we have a function looks like this. One is for business. All right, so the function is concave down, and at some point it changes direction and concaves up. So that point in which it changes direction and concavity, changes direction and curvature, that is known as a first sign of recovery. And now, usually when it comes to profits or revenue, we're starting to gain revenue and profits. And we started at a loss, but now we're gaining revenue and profit. So here we have the value of an item or whatever our stock is, or whatever it is that we're selling. The y-axis represents the value of that item. And the x-axis could be like, say, the time. Or like say years. It could be like the year, months, and so on, just depending what you want to display along the x-axis. So for a certain amount of years, we have loss, it is concave down, but at some point change direction, and after that point in time, it starts, our profits or values of our item starts to recover. Okay. But we can also have the opposites can occur. And the opposite is what we also want to look out for when it comes to business applications. If further investment of an item or of a stock, if further investment brings decreasing returns, like say for decreasing profit, decreasing revenue, rather than increasing, like it is with the first round of recovery, then this indicates what's known as the point of diminishing returns. Meaning this occurs when a function goes from concave up to concave down. Now we're starting to lose revenue or profit. Okay. So when it comes to business applications and concavity, we want to look for where our value is going to change from negative to positive, meaning where we have our first round of recovery, and then when we have a point of diminishing return, when it goes from concave up to concave down. Pretty much the opposite of what we see in this graph. All right, so this concludes here, section 3.2, using the second derivative to determine the curvature, the concavity of a function of x.